But as you can imagine, it was pretty contentious. For example, a lot of people didn't like the idea that the universe was changing all the time, and there was only one piece of evidence, which was basically that the thing was expanding, and the only people who saw that were people looking through telescopes. So there was a lot of discussion there. Before we go into the evidence, because there is more evidence, let's just quickly look at the maths, given that it's maths week. The maths was also highly dodgy, and the reason is because gravity, as you know, pulls in. Gravity didn't pull out. Gravity pulls in, as far as we know. Also, time in Newton's equation doesn't appear, and that would sort of make you think that time doesn't really have a beginning. And space doesn't appear either. We thought space was fixed. So the question is like, well, what the hell is pushing out then? And what's supposed to happen at time zero? How does it suddenly appear out of nothing, as people go to ask? Well, the answer to that is far from pleasant. The answer to that is, I won't go into this in too much detail, but the answer to that is there was a modern theory of gravity, completely theoretical idea that appeared in 1916 by no less a person than Albert Einstein. And what Einstein suggested was, in his theory, for purely mathematical reasons, was that space and time in general are not independent of each other, nor are they fixed. There's an overplay all the time between space and time. It's a very difficult idea, but he came at it for very deep reasons. Basically, space-time then, as a four-dimensional entity, is not fixed, and in fact, all we need to know about it was that it could be affected by mass. That what happens when you have something like a planet is that it distorts space. If you like to think of space because it's easier, it distorts all the space around it. And by distorting the space, if you look at the picture there, what happens then to anything going around that, see the little thing, suppose that's a moon going around the planet. The moon is forced to go around. It's an indirect thing. The planet distorts the thing, like a big ball sitting on a trampoline. The planet distorts the space, it's really space-time there. And the little ball runs around the planet because it's in this distortion, it's caught in this distortion. And that was a whole new idea, because that means gravity, in a sense, isn't a force in the normal sense. Gravity is simply some sort of a distortion, or some sort of a curvature of space-time. Now, I know that sounds like absolutely crazy talk, but it turns out that seems to be the way gravity works. That it's a distortion of space, if you like. It's easier to think in terms of space. It's some sort of a distortion of space. Now, before we go any further, I should say, scientists, again, they don't just swallow the stuff and say, oh yeah, that's a brilliant idea. We need evidence. And in fact, nowadays, there's very, very strong evidence that those ideas are right. The first one is, for example, gravity can bend light. Believe it or not, light going past the planet gets bent, and bent severely. And they have measured that time and time again. Another bizarre one is that time is affected by gravity. I bet you didn't know that, but most of you didn't know that. An hour is not an hour in a different gravitational field. So you've heard of, for example, GPS. Well, in GPS, the clock that's in the satellite up there does not run the same way as the clock down here, because it's not in the same gravitational field. It's a weaker one. We're very close to the center of the Earth here. We're in a very strong gravitational field. On the satellite, you're almost as far as you can go without being outside of it. So it's still in the Earth's field, but it's a much weaker gravitational field. And yes, if you take your alarm clock and you stick it up in that satellite, it will run at a different rate. And that caused a problem when they first started GPS, because the engineers didn't believe this. They had all the clocks up there and it didn't work. And the reason it didn't work was those clocks had to be corrected for the fact that gravity actually affects time. Very difficult idea. With some of these ideas, the only way to understand it is to look at the evidence, and then you say, well, it has to be so. Who knows why gravity affects time, but the truth is, it really does. Another interesting one you may have heard of is the most spectacular demonstration that space-time really is like this, is a thing called a black hole. And what happens in a black hole, incredibly, is that if you take a star and it happens to shrink down to a small enough size, the gravity field is so extreme that nothing can escape, absolutely nothing, because it pulls absolutely everything in. And that's because the curvature of space becomes literally a closed circle. That's why we call it a hole, black hole. And that's why, for example, you may have heard of Stephen Hawking. His importance is he has done a huge amount of work. He's probably the person most responsible for doing a lot of work in black holes and for showing that they probably very much do exist. And in fact, it's thought now that there's what they call a supermassive black hole at the center of every galaxy, not just our own, but every galaxy has a black hole at the center. Just an interesting thought. Anyway, back to cosmology. What the hell has all this got to do with relativity? It's got to do with the Big Bang, you might wonder. Well, now we have a theory behind us, because that particular theory predicts that the universe isn't necessarily static. The universe could be getting bigger, or it could be getting smaller, but the one thing it can't be doing under Einstein's theories, it cannot possibly be staying static. So that fits with what people were discovering. Now, funny enough, it was a man called Friedman, not Einstein, who saw the application of this to the universe. And those little 3 pictures there, what he's showing there is actually he worked out 3 possibilities. It depends on how much mass is in the universe. But what it could be is the universe either is closing, like see the bottom one there? That would be unpleasant. That would mean everything starts to move in, and eventually we'll have what's called a big crunch, that everything all moves in together. Another possibility would be at the top, that everything is blowing out so far apart so quickly that it'll never come back again. And then there's a sort of nice happy compromise where somehow the universe is beautifully balanced, where it's neither what we call closed nor is it open. It's just a nice little rate of expansion that seems to go on forever. And that's pretty much what we think today is happening. In fact, that compromise between flat and closed and open. And one of the big mysteries in cosmology today is, well, why is it so finely balanced between the two? By the way, I won't pretend that we know everything. For example, here you'll notice the snag, still a snag, of course. None of this explains what the hell happened at time 0. We still don't know, where did the Big Bang come from, if you like. One moment you have nothing, next thing you have this explosion of matter, space, and time. There's no getting around as what we call a singularity at the beginning. Okay, so that's the end of the maths. Now you'll be relieved to hear the rest of it's dead easy. That's all theory, and it's a kind of big ideas. But what about the evidence? Where's the real beef? Well, nowadays, let's have a look. We have discovered some other things which are very interesting. The first one we have already established. The expansion of the universe has simply been seen better and better with better and better telescopes, so there's nothing new there. However, well, we'll talk about that at the end. There is one big change. But another thing was, it turned out that the elements we see, you've heard of carbon, silicon, hydrogen, helium, the basic things that make up, do you remember the periodic table? You've heard of all those elements. Well, you can predict what elements you would get from the Big Bang. And we'll look at that in a minute. And the other thing is, it turns out a big prediction would be that there should be something left over from the explosion if it really happened that way. So there was a big idea. There should be something left over. Can we find it? Well, looking at the elements first, a guy called George Gamow, a Russian scientist, predicted that actually, if this really happened that way, and there's a picture of the Big Bang up at the top, if the theory is right, our universe should be about 3/4 hydrogen and 1/4 helium. And you might be surprised to find here that that's actually right. We're not talking about planet Earth now, we're talking about the cosmos in general. And it is 3/4 hydrogen and 1/4 helium. What about the rest, all the other stuff? Well, it only makes up a tiny, tiny fraction. So it's the main stuff of the universe is hydrogen and helium. And that was observed, so that was immediately a second pointer. Here's our second plank of evidence that this crazy idea might just be right, because that's what the evidence says. Just as a matter of point of interest, where does carbon come from then and all the other stuff? The answer is yes, it's formed from the stars. You've probably heard this thing that we're all made of stardust. We're all made of dying stars. That's actually true. It is. As a star dies, it goes through this incredible nuclear fusion. It fuses every element. Hydrogen goes to helium, helium goes to carbon, carbon goes to silicon, and it runs through every element in the periodic table, and then just blows it all out to supernova. And that's what we're made of. That's what planets are actually made of. But that doesn't get around the fact of where does the hydrogen and helium come from in the first place. And the answer is it comes from the planet. So it is true that we are made of dead stars, but what's much more interesting is that the universe is mainly made of hydrogen and helium, and that comes from planets. But what I think you'll probably find more fun is, what's more fun in a sense is a much more dramatic prediction is if the universe really did begin in this explosion. And by the way, I forgot to mention, even Einstein didn't believe this at first. A lot of people didn't believe it at first. But if it did, there would be some radiation left over. A bit like if you drop a bomb in somewhere, that there's radiation going on, especially a radioactive one, there'll be radiation going on afterwards. Same thing with the beginning of the universe. There would be radiation left over. It would be everywhere, because the Big Bang happened everywhere in space and time. It would have a certain, what we call a certain type of spectrum called a black box spectrum, and it would be of a certain temperature. And that was a prediction again made by Gamow and his group. And that was a very interesting prediction that everybody ignored. For some reason, people just didn't really think this was important. This was made in the 1940s, and they discovered it by accident 20 years later. 20 years later, these guys built the world's first radio telescope. A radio telescope is a telescope that works just like a normal one, except instead of looking at visible light coming out of planets, you turn on your radio basically, but it's a very special type of radio, and you listen to radio waves. They built the world's biggest radio telescope. They were looking for something in particular, and they kept getting this stupid interference pattern, and they couldn't get rid of it, and they spent a year, like good postgraduate students, they spent a year working on it, trying to take out every single piece of circuitry, trying to fix it, and they simply couldn't get rid of it.